Okay, so just want to make sure everyone can see the slide, right? So can you see the slide on the screen?
Yes.
Thank you. Oh, I see a student want to discuss about the project, right? So yeah, so we will find time to discuss the project. Maybe later we find a particular class to discuss the project. Okay, so if you have a question right now, you can ask me because we are still waiting for some students. Right.
So, Professor, I'd like to ask about the environment setup for the project. So I was trying to implement mask RCNN.
Yeah.
I was referring to the Matterport GitHub. So the one thing which I was facing is the environment setup. So I've seen your code where you have converted TensorFlow 1 version to TensorFlow 2, but
Yeah.
I could not find the requirements file because due to the change in the version of Python and other modules like TensorFlow, Keras, and everything, I was not able to run that. So
I see.
need some assistance with that.
I see. So I think let me see. So are you saying that you build your own model, or you are using the model that we pre-trained? You cannot run it.
Yeah, I mean that was a different issue which I was facing because Nav, Collab, and everything are using the TensorFlow 2, and we were trying. I was getting into a lot of troubles with that one because when I changed the default TensorFlow version from 2.x to 1.x in Collab, some of the functionality is not working because I'm not really sure. I'm still looking at Stack Overflow and other solutions.
I see. Let me share my screen. Yeah, this could be an issue. Let me see how to do that. Just one moment. I think we can still use that screen, but just one moment. Let me stop here and.
I am also interested in knowing if anyone had the same issues or were able to solve the issue.
I see. So let me pull something here. Just one moment.
Talking about the homework, I'm trying to use Python on it, and I'm not sure how to do the derivatives.
Oh, so just the one. So the derivatives, just one moment. There's a bit more stuff. Let's do that one by one. Okay, clarify them one by one. So you can see the browser here, right?
Yes. Yes.
Just I think I should let's see. So for the assignment, if you want to take derivative, actually you already took derivative if you finish your written assignment 1. Okay, let's take a look at the written assignment 1. We will release a solution shortly. Okay, so yeah, if you look at here, question number 4, we asked you to compute the Hessian, right? So the Hessian matrix, right? And in the meanwhile,
I wasn't able to do that.
What?
I wasn't quite able to figure that out. I'm sorry.
So you cannot answer this question basically. Are you saying this? Hello?
I tried, but yeah, I tried, but I couldn't get there.
Yeah, but we actually give the solution in an earlier video, right? So did you watch that video?
No, I did not.
Let me see. Yeah, let's go through these things so that it will be it will be clearer to you guys. Okay, because the deadline is approaching for the assignment. Right? So firstly. If you look at our Newton's method, okay, and we ask you to follow this slide 44 to 50, right? So if you look at slide 44 to 50, it will load for a while. Okay, so in the meanwhile, let's look at here, right? So basically, derivative is what you should have already done in assignment 4. Okay, assignment homework 1, question number 4, where in one of the slides we already show you. Let's say you have the loss function and you have the error function, which is a likelihood function and error function. Right? They are kind of logarithm. Okay, so log of negative log likelihood is the error, right? And it becomes cross entropy loss. And for this error function, which is for logistic regression, we already show you how to take the derivative, right? So which is the gradient. Okay, so you have gradient, and in this question, we'll ask you also to compute Hessian, right? So no matter gradient of Hessian, it's already taken. So once it's taken, it's actually a function like something like this here, right? So you can directly take your true label and your predicted y, which is computed by this kind of sigmoid function, and it also has the else row and the trace column attributes, right? So these things, once it's computed, it's just a mathematical function, right? So you don't need to take derivative anymore because it's already computed. This is one thing. And then if you look at here, we set a 44.
Hey, on there,
yeah.
To make it the Hessian, do you need to compute the derivative with respect to I? Do you need to do another partial derivative, or am I wrong?
Exactly. So you just follow this derivative to another derivative, right? So, and if you look at a 44 here, so basically all we ask you to do is implement this thing, right? So this is a Hessian, inverse of Hessian times the gradient. Gradient is given to you, and Hessian is just taking another derivative, okay? And then you will have these two things, and you can just do a inverse and do a multiplication in NumPy, right? And then that's it, right? So I mean this update here, okay? So you keep doing this. Of course, this is not x, this is the weight, right? So, but it's just the parameter here, right? So once you do this, I mean, if you know this answer for this is already in the slide. This should be not so difficult to do. So this is all we ask you to do. So when you answer this assignment, basically we are asking you to get the Hessian from question number 4 in the previous assignment. And then you know its form, then you can take inverse and time the gradient, right? And if you look at so we do share the video. If you look at, let me see. Yeah, I see not all students are going back to watch the video, right? So, but we do share them every time. If you look at here, we have today's video with different kind of links, right? So today's video, each class we do share the video, right? So if you look at the video here, basically it's all shared under the same channel. Okay, so let me go to the channel, and there is a particular channel. No, not channel, a playlist, right? So there's a machine learning playlist, okay? Why? And if you look at a particular one that we go through it, I don't remember which one. Maybe we should explore a little bit, but it's definitely there. Okay, so we do take the derivative. Yeah.
I think it's 10 years.
It's this one, right? So yeah, we already take a derivative for you, and then we have all the derivation for you. If you were in the class, you should be able to do that. Okay, we will show you the answer basically in some way. Right, we continue to take this second derivative, and basically we are pretty much close the gap for all of you guys. So you just watch this video, and you will know how to what's the answer. Okay, we will release the complete solution. Okay, this is then you have Hessian matrix form, right? You show that it's positive semi-definite. Right? So that's it. It's okay, Peter? You answer your question?
Yeah, for the most part, it's helpful to see which lecture. Yeah, it's still difficult to see what the text is saying, but I think I have enough to go off of.
Yeah, if you go through this video, probably will understand it, right? So, yeah, okay, yeah, it's lecture 10. Okay, so in our shared video, right? And this is one question. The second question is about Mascasian, right? So let me get the folder.
Professor, so I implemented Newton's method, but the problem I face is that it's mostly stuck at 88% accuracy, but with cross-validation, sometimes it would go 95%. So I'm not sure why that inconsistency is happening. Could you maybe
I
share
would
some
think that
insight?
the accuracy looks very high, but actually it's not doing well.
So if I, so on average, it's like 88% accurate, but if I do k-fold cross-validation for 10 splits, sometimes it can go as high as 95%, but it's not consistent. That's what I'm saying, that's the issue. On average, it hovers around 88% in accuracy.
Oh, I see. So you can, I'm not sure, but usually it's larger than 95%, or at least around 95%. But you can try with the other, the built-in logistic regression module, okay? And you see how different they are. Maybe it's because of the, their logistic regression module has, let me show you something.
So with the built-in module, with the Newton's method, I can get like 96% always.
Yeah, so basically if you look at logistic regression scaling, right? So one thing you need to pay attention is their logistic regression model. Of course, you can debug by setting their model. Of course, you cannot just do this. Okay, you need to implement your own and compare with this, right? So you can set their model to be Newton method, okay? And then you debug. But one thing you need to pay attention is there's a penalty, which is the L2 norm, okay? They add a regularization at the end, which can be none, right? So if you are implementing a none, then you need to set this to none when you do comparison. Okay, if you add a regularization, maybe that's one reason they are doing much better. It's okay? Yeah. So basically, if you want to do L2, you need to change our formula a little bit, right? So you take derivative also to W squared, right? So and you implement that L2 version. Okay. Otherwise, you just set it none and see how the performance compared to each other. Right?
I see.
If you see it's similar, then probably implementing the same. It's okay.
One more thing I observed is that after one or two iterations, the log loss would become NaN or not a number. Maybe it becomes too small.
I don't know why, because this is a convex function, right? So this should not happen. Maybe there's some bug you need to figure it out. Okay. Yeah, and these L2, L1 are also convex. So it should, when it's convex, the Hessian matrix is always positive, right? So positive, non-negative. Okay. So I'm not sure why it will go to.
My Hessian matrix becomes all zero after a couple of iterations. When it becomes very low.
Yeah, then that's converged. Basically, you should have a stop criteria, right? So let me see. I think
even when it converges, Hessian becomes zero. My predictions are still not like over 90%. It's like 88, 89%.
Then maybe that's correct. You just try without any regularization whether it will achieve 88%. Okay. If there's some difference,
I also observed the same thing, Professor. But when I tried to tweak the data, like the after the split, the quality of the data, then I was getting good accuracy.
Oh yeah, so there's some missing value, right? So there's a question mark in the data, right? Is there a question mark in the data? Yeah. So this you need to use the pandas. Okay, the pandas. We did not go through it because we want to leave that to you guys to explore. But when you read the data, right? So for example, you CSV, there's a way you can specify. For example, there's a NA values. Right? So this thing. Let me copy. NA values is saying that. Let me see. Is basically you can put it. Let's say our missing value is a question mark. Then you can say, hey, this string is question mark. You say, hey, question mark is not available value. Okay, and then you can clean the value using average value or anything. Right? You can do some data cleaning using fill NA in pandas. Okay, because this is pandas, right? So fill this value with average or something. Okay. So you can Google a little bit how people do this kind of data cleaning and how they feel. Right? So yeah, that may be helpful if you, let's say you do things like not clean the data in different ways. Maybe that will impact. But as far as I know, there are not too many data with missing values. Right? Most data are there. So you can try to see how, like what's your data cleansing that to make it improve?
So with the way I cleaned it is just I just found out all the question marks and replaced them with 0. But I think taking an
No,
average
that's
would be
another
much.
good way. At least take the average. Okay, right. 0 doesn't make sense sometimes. It's okay. Yeah, takes a column average and fill it. And yeah, so that's pretty much so the QA. So because yeah, another thing I forgot to mention, right? Mask Cassian. Okay, so Mask Cassian, we share the code online, right? So if you go to, let me see, announcement, I think it's in announcement, right? So I think we share the code. We have some annotation file that are, unfortunately, people are not using polygons, and that caused our pre-processing code to throw an error. So we will release the data next week, okay, next week, because some students are still fixing their annotations. So then you will be able to use that data to do the cleansing and to train the model. Right now, you can use some subsets that are already working, okay, all using polygons, for example, to pick out some to make the model run smooth. Okay, and we started the self-registration. I think that the documentation tells you how to register for the group. And for the TA hours, we have set it up like this. So we will have a bunch of chat rooms, like breakout rooms, and TA will be in the first room. When you get in, you can talk to people, okay? And then you can say, hey, we want to probably discuss more privately. You can find a room and go and discuss, right? So this is a way that you can find your teammate, right? So just try to join the office hours from TA, not just to talk to the TA, maybe also talk to people who want to form groups, okay? We have 50 groups, but once your teammate decide, hey, we will probably form a group, just find an empty group and join, okay? So you can self-register together, find an empty group and join, right? And we do require you to discuss with your teammates before you join that group, okay? Otherwise, probably we will kick you out of the group if the other teammates complain, okay? So this is what, but you can do individual project for sure, okay? So this is one thing. The second thing is that I think we have a sample solution, okay? We have a sample solution here. And you can download it. It's basically a trained model that you can directly use the model, load the training weight matrices to your model and do the testing, okay? And in there, so if this max sizing by default, it only takes TensorFlow 1, okay? So it only takes TensorFlow 1. But if you change, this model has been compatible, this model.py has been revised to be compatible with TensorFlow 2. If you want to run with TensorFlow 2, which is now the default in most of the cases, right? If you want to do that, okay, then you should, let me see. Then you should use this version, right? In TensorFlow 2, we will help you route to TensorFlow 1 and a lot of other operations, okay? Just to replace the model.py from their, online, GitHub with this file, model.py. Replace this model file with what we share, okay? And that will solve it. And what's your question? I cannot hear. Yeah, so your signal is not very good. Yeah, how about this? Let's chat maybe during the break. Okay, we need to move on. Right, it's already 20 minutes, and you can see whether the signal can be fixed, because right now we cannot hear you clearly. Okay, then, so yeah, it will take time for sure, right? So, but think about it. This kind of project is useful, right? After, let's say, you graduate and you go to a company and they do want you to use a tool, right? After you know these concepts, right? Supervision and classification regression, those kinds of things. You work on a real project and you should have the capability to do this, right? So this is just a one sample project to see whether you guys can accomplish, okay? Okay, let's continue then. Yeah, and we probably will discuss on this more later if we can finish, all the slides earlier. Okay, so because we still have a lot of things to cover in this course, and we have another written assignment to go. Okay. Yeah, today we will talk about the support vector machine, right? So, last time we have already seen, right? So let's say you have two lines. Let me take my red pad, okay? Just one moment. I need to configure my pen a little bit. I think now it's fine. Yeah, so yeah, now it's working. Right, so you can draw a line somewhere, right? So you can draw it here, right? And you can also draw it here, something like this, right? And you can even draw it here, okay? So this is very dangerous, this line, because you shift it a little bit, you have misclassification, this becomes a blue class, okay? Which is wrong, okay? A safe line should be the one that maximizes the margin, right? So you have some distance to each side. But these 2 points are special, okay? This is called a linearly separable, okay? There are certain cases that are not linearly separable. You think about this becomes, let's say this becomes blue, then it's not linearly separable anymore, right? Because this is in the middle of the brown rectangles, okay? This can happen because we maybe mislabel, okay? Someone mislabel this as a blue circle, okay? Another possibility is that your label is correct, but your x1, x2 is a little bit shifted, right? You shift to the other side a little bit, right? So very close to here, you may have some noise, okay? So we have explained last time that we don't like these two lines because they are not safe, right? You shift a little bit of the A and B, right? AX plus B, right? The weights. Then you have misclassification, right? So this is a safety case. Here we are only considering that two set of points have some margin between, which means they can be linearly separable. Okay. So we need to define a target function, right, for finding this line, right? Because all branches of machine learning is just like a optimization, right? So we want to find a target function so that we can tune this line AX plus B, right, A and B values, so that it maximize the target function, right? Here we want to maximize this so-called margin. Okay, so what is the margin? So margin is basically, you think about it. Last time we also derived this this formula, right? So what's the distance from a point to a line, right? In general, in high-dimensional space, it's a hyperplane, right? For a point to a hyperplane, what's the distance, right? If you compute all their distances, okay, and you pick the closest one, right, which is this distance, right? The smallest distance to the line should be maximized. Okay, so this smallest distance called the margin, and we want to maximize this margin. So basically, you want to maximize the distance from the data point closest to the line. You want to maximize this distance. Okay, so there's kind of minimax kind of thing, right? So firstly, you want to find the minimum distance among all the points, but that minimum distance we want to maximize. Okay, so maximize this margin. Right? Any questions? So yes, there's a relationship between margin and generalization, right? So in learning theory, people prove that larger margin generalize the best. Okay, so there's a complicated mathematical proof, but that's not important. Just to keep in mind, if you have a large margin, your line will be more safe. Okay, because if your line is something like this with a very small margin, then shift a little bit of the A and B, you have a misclassification. Okay, this becomes a problem. So in the ideal case, let's say we have two sets of lines and they have some distance in between, right? This we call it the hard margin. Okay, this is a hard margin support function. Okay, and as we will see later, so some of the data points cannot be linearly separable. Okay, in that case, we have the soft margin, right? This is a must if two set of points are not linearly separable, because you think about it, right? So if let's say this point is blue, right? Then it's become complicated, right? So you have no line that can separate them, and this margin becomes negative, right? If you think of this side is blue, this blue point will be negative, it could be here, okay? So we do need to relax it to consider mislabels or small noise or classification, okay? Okay, let's continue. So the hard margin case, basically, we require that two classes are assumed to be linearly separable. Okay, if they're not separable, this case does not apply. We have no solution here. Okay, so we assume that if really we can draw a line, right, like this line, okay, to separate these 2 points, right? So we can draw a line, and this line separate the group points and the ground points. And if you move this line along this W direction, remember this W actually is decides the direction. So if you look at the W, this is the W vector, which is perpendicular here. Okay, if you keep this W and just shift around it, right? The first time you touch the brown points, this is the margin on the brown side. But if you shift to the other side, the first time you touch the blue points, okay, so this is the other side, right? So then you will find the smaller of them, and they become the margin, right? And in this example, in this particular example, when we shift, actually, of the same distance, we have this point, maybe this point, and this point. 4 points are all on the same margin, right? So it's looking very unlikely to happen in real life, right? But this is in a linear case, right? So in later we will see that we will extend this to more complex case, okay, using kernel methods, right? In that case, will have a small number of so-called support vectors, those kind of points on the boundaries. We will see that later, okay? Because this is called a support vector machine. So we'll see the details later, okay? So with proper scaling of W and W0, right? So you can make sure this side is 1, okay? This side is negative, which means when you touch the closest point, when you shift it, right? So keeps the direction, right? The first time you shift, there may be a bias, maybe A, but you can normalize it, right? So for example, if you shift here for a particular W right now, you say, hey, this is A, this is not B1, right? So what you can do, you divide our A and W10 also divide by A, W also divide by A, right? So this is a vector divided. And then you can scale it, right? After scaling, you will get this, right? So we'll always stick to this. In the assignment, you will show that even if it's A, you will get the same conclusion. We are not simplifying. So this one is just without one, you can also do that, right? So you can always scale it, by the way, right? So if you have a large W, right, so make the A, you can always scale, okay? So they are equivalent before scaling or after scaling, right? And such a hyperplane is called a canonical separated hyperplane. Canonical means that we scale it to 1, okay? Because if you think about this line, okay, so let's say you can times this W by any parameter, let's say AW, right? This is AW0, and this becomes A. That's also a valid line. Okay? This is the scaling, okay? Right, so it's the same line, basically, okay? So you can scale anyway, right? So we do need those canonical form so that it's become unique, right? So basically we set this to 1. Now let's look at how the next question is now assume we already normalize this W vector and W0, right? How can we represent this margin in terms of function of these weight matrices, okay? How can we do that? This is what we are talking about in the next slide. So what we can do is this. Let me call out my pen. Let's assume, again, this is the 0 point, right? So the WT plus X plus W is 0, okay? This is the one side, okay? This is the negative one side, okay? Right, so now we assume X1, X2 to be the closest points, 1 on each side, right? So when you shift, maybe X1 is here, okay? And shift to the negative side, maybe X2 is here. Let's move a little bit up so that we can show things clear, okay? So these are the 2 points, right? So that's why we say the WX1 plus W0 is 1, okay? And W2 plus, on this line, the value is negative, right? So this is what we have right now. Now let's take a look at this, okay? So if we minus these 2, right? So this equation minus this equation, this will be 2, right? This positive 1 minus negative 1, right? And this W0 cancels. And this is, WT, W transpose is the coefficient taken out. and these two vectors minus. Okay, it's an inner product between these two vectors, W and the difference vector. Okay. Now let's take a look at what does this mean. Keep in mind, W is what? W is a unit vector along this direction of the line. Okay, the perpendicular to the line. Okay, this is the W, right? And what is x1 minus x2, right? So you know, this is something like such a vector. Okay, if you cannot see that, you just see that if you have the origin node, right? O x2, right? So plus this direction, O x1. Right? So basically x2 plus this thing is x1. So this thing is x1 minus x2, right? So if you want to see why this is good. But anyway, so when you minus two vectors, it's really the vector connecting them, okay? And so now what we want is really this distance, right? This distance here, right? So, you know, this is basically this length, which is here, this vector length, and project it along this direction, which is this direction, this W direction, okay? This is the unit vector. So this is like this guy times cosine theta, right? So we get this distance, okay? But what is this? This is twice the margin, okay? This is twice the margin, right? So now we know that this thing is, you know, something like here, okay? Something like, again, so W, previously we say we will normalize W, right? Here we have not normalized W yet. We will normalize W so that, you know, this becomes a unit vector, okay? This is a unit vector. Okay, once we normalize this W like here, then we times this thing. This will be this margin side. Okay, and because this is twice the margin, we only need one side, right? So we'll divide by 2. Okay, and an important point to keep in mind, this is 2, right? So here, okay, 2 and 2 cancels, and that's why it's just a 1 by W. Right. So the conclusion is actually quite simple. The margin is actually 1 divided by W. There's nothing to do with W0. Okay. Right. So when you want to maximize this margin, you minimize this W. Is okay? Yeah, because previously we were working on that diagram. It's a little bit confusing. Let's go back to this diagram and show this whole thing again. Okay. So firstly, we have x1 here, then we have x2 here, right? So we are computing their difference. Okay. But we do care about this margin here. Okay, this margin. Right? This is gamma. This is another gamma. Right. So this is 2 gamma. Okay. And now what we do is we times this with cosine theta. Right. So to do that, we just take the inner product along this direction W. Okay. But this W has to be unit vector. Right. So otherwise, you know, it's cosine theta times, you know, the length of the 2 vectors. Okay. So one vector should be 1. Then it's just simply this length times cosine theta. The other length is 1. Right. So in order to do that, we need to take the unit vector. Right. So take the vector length. Okay. So once we do that, it's equal to 2 gamma. Right. So this is what we have. Okay. Right. So if you move this here, the 2 gamma is really this. Right. So it's like no, not this. It's really this difference factor times the cosine theta. Okay. Any questions? I hope this is fine. Okay, so the conclusion is very simple, right? So when you want to maximize the margin, right, you just minimize this step, right? Because it's you know, at the denominator. Okay, when this is large, basically you make the denominator smaller. Keep in mind this is a non-negative value. Okay, it's a positive value. Because if it's 0, it doesn't make sense. Okay, it's the not negative. And let's revisit our requirement. Okay. So we know that this is maybe it's a 0 line, right? If we shift to 0, we have 1 line, okay? And we shift to the other negative side, we have -1, okay? Right, so, but what do we want? Let's say we want these objects to be on this side of the plane, right? We want to have some margin between these 2 points, okay? We want the other set of points on the negative side of the plane, okay? So put simply, what does it mean by on this side of the plane? Right. So this means this thing should be larger than equal to. Okay, you are on the larger than equal to side, right? And in the meanwhile, what does it mean by the positive sign? The positive sign means the y is 1. Okay. In support about machine, positive is 1, negative is -1. Okay, not 0. Right. The reason is very simple. You will see that we do need the -1 to close the gap in this definition. Okay. And now let's look at the other side. Okay, because there's nothing in between. The other side basically says if you want to be on the other side of the line, this thing should be less than or equal to -, right? But in the meanwhile, your y is also negative, right? So this is the negative sign. Okay, so your y is negative. Yes, this is the conclusion we just derived. And it's not difficult to see that the combine basically is giving us this constraint, right? So this thing times your y should be larger than equal to, right? If you cannot see that this, I think it's pretty intuitive, but maybe positive side is more intuitive, right? Negative sign may not be that intuitive. Think about if what is negative, less than -1, at least maybe -1.5, right? And if you then this value times -1, this becomes what? This becomes 1.5, right? It's larger than. Okay, so basically combine the two. So a key observation here is that they are equivalent. Okay, this thing and this thing is equivalent. We can use a simpler form to that, right? Any questions? I hope I'm not too fast. Okay. Yeah. So actually, when we require this larger than equal to 1 is exactly our margin. We want to have some size 1 margin, right? So you don't have anything in between. You're on both sides. Okay. And actually, this may be too strict, right? So if we allow something in the margin but still correct, right? So you have some positive sign on the other side of the 1 line, but not go across the negative side. Like this is 0. Okay, that's also fine. Right? If that's the case, basically we can reduce 1 to 0. Okay, so but we now instead of using this loose constraint, right? So this loose constraint is basically saying that if you are larger than equal to 0, you are positive. But if you are less than equal to 0, you are negative. This is a regular expression. But instead of using this, we are executing this. And this exactly is the margin we want to execute. 1. Okay? This is the margin, the line value. Okay? Negative. So this is the intuition that you can get. So if we just use this, it's just require you are on the right side of the plane. Right? So basically what we are talking about is here. It's fine if your brown rectangle is here, right? It's as long as it's not on the other side. Right? This is 0. Right? That's fine. Right? So that's the other requirement. But it does not generalize well because the margin is smaller. Okay. So here we do require the data points. If we only require this, it's just on the right side of the hyperplane, right? But it does not generalize, okay? Because we want some distance away from hyperplane. Any questions? Okay, so here is our problem definition, okay? So this is our constraint, right? This is our constraint. The constraint should be met, right? Means they are linearly separable. One on the positive side, larger than 1, one on the negative side, smaller than negative 1. Okay, this is a constraint. And our target is minimize the W vector length. Okay, and minimize the W vector length is fine, right? But it's equivalent if you say it's a square of that, right? So if you minimize W, we also minimize W squared, right? So we also do a 1/2 because when we take derivative, this 2 can cancel. So for just mathematical simplicity. Okay. Now the reason we want to, yeah.
Sorry, I'm not convinced where the square came from. Square part, weight matrix, you're squaring it again.
Oh, okay. So square part, right? So yeah, so for example, let's say this is a non-negative value, okay? Let's call this x, right? And what is x squared? Y equal to x squared. It's this shape, right? So that basically says if your let's say you have one value W1, W2, right? So you have W1 and W2, okay? For any W2, this is smaller than, right? Then here the W1 square, W2 square also keeps the relationship, okay? This is monotonic increasing. So when you minimize, you find a W that minimize your W itself, you also minimize the W square. Is okay?
Yes.
Yeah. So this is trivial basically. When we add a constant or we square or cubic, as long as it's monotonic, so then you can change this target function, whatever way you like. Okay.
Thank you.
Okay. So we are changing to this shape because we want to make it mathematically easy to handle. Okay. Let me clear the drawing a little bit. Oh no, I think because I'm not doing this. Yeah, so I have to clear. Yeah, I have to clear this one. Okay, so yeah, so this is our problem, and why we wanna make such a problem, right? So why we don't write just minimize W? We want to do this, right? So this quadratic make it a so-called quadratic program, QP problem. Okay, so you may not be familiar with a quadratic program, right? But you must be familiar with a linear programming. Okay, so linear programming means your target function is linear, right? A quadratic programming just says your target function is quadratic. Okay, the constraint is still linear, by the way, right? So this is the parameter because these are constant. So this is constant times W1 times W2. So those W's are linear. Okay, coefficient maybe x1 times W, right? With y. Okay, and the W2. Right? So this is a linear constraint, but the quadratic constraint for the optimization. Okay, this is called the QP problem. And why we care about those kind of QP problems, right? So let me see. Maybe we can search for LP, QP, QC, QP. Let's see this kind of thing, right? So so in convex optimization, right? So there are a set of problems that are well defined. Okay. So for example, linear programming, right? If you can formulate your problem to linear programming, then you can use a linear programming solver to solve it, okay? If you can formulate your problem to quadratic programming, right? So then you can use a quadratic program solver to solve it, right? The rest of the computation optimization, you just leave that to that solver, okay? And there are also QCQP, right? So QCQP is saying that not only the target function is quadratic, okay? Your constraints are also quadratic, okay? So right now our constraints are linear, if you look at it. And there's also second order OCP, SDP, there's a lot of preset solvers that you can use. Okay, let's take a look at some of the, let me see where my mouse. For example, linear programming is saying that your constraint linear, your constraint linear and your target is linear. Okay, this is constraint. And you can also import. And the QP means your right now you should know what is quadratic, right? So this is quadratic form. Okay, this is linear component, this is constant. Okay, the target is quadratic, your constraint linear, right? This is QP, right? And there's also called QCQP, right? So constraint quadratic, right? So this is a target function, and your constraint can contain some quadratic constraints in addition to a linear constraint. Okay, so the reason we wanna have this. Of course, when you talk about QCQP, it's also QP is also QCQP, right? And if you look at the linear program, it's also QP, right? So just the quadratic term is 0 here, right? But each solver will be more expensive to run, okay? And there's one, particularly in Matlab, you have the Matlab CVX, that's a convex, okay? So the package. Okay, so I think Python may also have such wrappers, but so basically this is a particular solver that you can use how to do program optimization, etc. Right? So So right now you don't care about it because we are using scikit-learn. So scikit-learn, SVR, SVC, right? So classification is SV classification. Otherwise it's SVR, right? So down there they are helping us to do this. Okay, they are running the libsvm library. Okay, right? As we said, Python is a wrapper. Okay, so libsvm is actually, I think, by some Taiwan people in C++. Okay, originally Python wraps it. Okay, Matlab is also wrapping. Okay, so it's actually originally in C++. Okay, and they have some Python wrapper on that. Okay, so I think they have a lot of languages maybe, but I think the original code should be in C. Okay, and so yeah, we can look at the GitHub. Yeah, C or C++. Right, so obviously it's larger than Python support. Okay, I'm surprised they have Java support. Maybe they have another version of Java. Okay? And if you look at
现在台大做的
对
LIBSVM，
yeah, exactly. Yeah. I think it's very famous, right? So basically everyone is just using their tool as a shell. Okay, so just using them as a shell. If you use a Matlab, it's actually also running this because these kind of tools are true research, right? So and all other libraries are just wrapping them so that you can use them easily. Okay, following Python API for scikit-learn, etc. Right? So using NumPy array. Okay, but down there they are running this kind of code. Okay, so reason again here just to give you a little bit more knowledge on that, right? So anyway, so we are just trying to formulate this problem into a QP problem, right? That's why we need the quadratic. Okay, right? So yeah, so this is a linear constraint but quadratic form, right? So why we need a quadratic? We will see that later. Okay, when we take the dual form, etc. Okay, there's some reason that this makes the derivation a lot more easier. Okay, and by the way, they are not using the solver. I think they write their own solver, which is more efficient. Okay, and in optimization theory, it's advantageous to turn a primal problem into dual problem and then solve them in the dual form. Right? So one particular example we have seen is the Lagrange method you have seen before. Okay, right? When we review the mathematical background. Okay, and let me see. And so in our case, actually, we do want to go to the dual form, right? So why this is the case? Because when we play with SVM, except when you are using some like linear SVM, right? So a lot of web, how to say, doing the web mining, web search engine researchers, right? They create a lot of features that are like a click-through data and stashing data, etc. Right? You may define maybe 50 features. It's still very high. Okay, but usually we will use some kernel method. We will see later. Okay, we will map it to a very high dimensional kernel. Right? So maybe it's 1 million dimensions. And there's the RBF kernel, which is by default in, we can take a look at here, okay? Let me, RBF kernel, right? So SVC, maybe, we just look at SV scaling, okay? So if you use scikit-learn, by default, it's not using your linear kernel, it's using the RBF kernel, okay? We'll discuss this later, okay? This RBF kernel, by default, will map your original data dimension, maybe d-dimensional X, to an infinite dimension space. It's literally an infinite dimension space, okay? So in that case, you cannot handle that, right? So if it's infinite dimension, if you take in the product, right? You take the x1, y1, x2, y2, x3, y2, you need to do infinite times, right? So that's not easy to handle, right? So when you convert this problem from primal space to dual space, okay, this problem is no longer depending on the feature space size, okay? It depends on data space size. And I understand it's a little bit counterintuitive if you don't look at SVM, okay? Because if you look at the other models, right? So usually you have more data than your features, right? So the rows are more than the columns. Okay, but here we are really looking at, for support back machine, the strength is really looking at the case where you have so many columns, but you don't have too many rows. Okay. And before, let's say the deep learning you know, there's an AI winter saying that if you remember last time we talked about neural network, there's exclusive role people can find it cannot do, right? So that's kind of triggers something so-called AI winter where neural network models are kind of dumped by people, and all people are just moving to support vector machines. Okay, but again, support vector machines are not so powerful as neural networks, right? But they are easy to handle, right? So by that time, basically everyone is doing support vector machine. Okay, during the AI winter period, this becomes harder. Okay, because you can translate your limited dimension to an infinite dimension. That's way powerful, right? So that's a very powerful tool we will look at. Okay, so the dual form also makes it easy for, the first reason is that in the dual form, your computation no longer depends on D. Okay? If D is a vector, like D dimension, which can be infinite dimension, right? At least let's say 1 million dimension, right? But maybe you only have 2,000 data items, right? So now in the dual form, the computation really only depends on 2,000 if you only have 2,000 nodes. Okay, that's why actually people want to go to the dual form. Okay, and there are also it's actually very easy to solve in the primal form. Okay, so if your dimension not so high, maybe primal form is more desirable. Okay, so recall that we talked about Lagrangian, right? So Lagrangian basically is something, where we say that you want to convert a constraint, like we have constraint optimization problem into an unconstrained optimization problem. But in order to do that, we have two steps, right? So the first step, make sure on this side it's 0. Right? So basically you want to move this to -1, okay? So this thing -1, right? And then you say, hey, this is the target function minus a Lagrangian multiplier times this constraint, okay? Right, so this is what we see before. But that time, this is equation, right? This is the equal. This is not inequality, right? So actually, Lagrangian can be extended inequality, okay? And actually, we discussed about that earlier before. Again, those mathematics are a little bit crazy, and we do not require you to create new optimization ways, but you need to understand the steps so that you can do the assignment, right? The assignment will be just a small change of those steps, okay? So when you have inequalities, okay, then Lagrangian multiplier cannot be any value, okay? There's a sign requirement on it. Let's take a look at this requirement, okay? I think we can look at this link. Why it's so small. Right. So previously, when we talked about the Lagrangian method, we only have, let me call the pen. We only have, this target function and this equality constraint, right? So for equality constraint, you can move to, Lagrangian multiplier for each constraint, right? Now we also have inequality constraint, okay? When you have inequality constraint, it's kind of similar. You also have Lagrangian multiplier, but this thing has some requirement, okay? And why, actually, if you want to understand why, you can read that dual form chapter in Stephen Boyd's book. That's probably one of the easiest chapter you can read, okay? It's very detailed, you will understand if you have time, but we do not require you to do that, right? So that's not a prerequisite for this course. Whenever we need to use that, we will tell you, okay? So here is the requirement, okay? So maybe I should move this up. How to make it smaller? Just let me. Yeah, so we need to show all these lines, okay? So when you have inequality constraint for those H, so H will introduce those Lagrange multipliers, right? And those Lagrange multipliers need to subject to the fact that they are non-negative, okay? So there's proof that these two are equivalent, okay? When you convert to an unconstrained problem, it's no longer a total unconstrained. You have another constraint for this newly introduced Lagrange multiplier, right? If you ask me why, you can read that chapter, I think, in Stephen Boyd's book, okay, in complex optimization. Here we are just applied mathematics, just to keep the conclusions so that you understand, we help you understand the conclusions, okay? All right, let's continue. So in our case, you see this constraint is what we just derived, right? So move the 1 to the left-hand side, right? But you see that difference. This is minus, right? This is minus, okay? This is plus, right? The reason is very simple. If you look at this sign, this is larger than equal to, but here, this is less than equal to, okay? So if you are less than equal to, then it's basically saying something like you can take the negative sign, right? Then it's negating this constraint. That's why we need a negative sign. Otherwise, it's just the same, right? Any questions? If not, let's continue. Right, so again, I know it's maybe difficult to some students, but just to follow this and you get a familiarity with how people do these things, right? So that's why everyone's using libSVM, right? It's designing new stuff is not so simple, okay? Right, so unless you are super familiar with optimization, okay? So this is the target function, right? This is the constraint, right? The margin 1, okay? And this is the Lagrange multiplier, okay? And because this is an inequality constraint, right? So we do have this requirement, okay? Right. And now we can you know, compute it one step, right? So this is minus this summation over 1, right? So 1 times this is 2, right? Minus minus, it will be plus. So you get this term, and this term is just you know, the other term, okay? And now we can further, you know, because we know that L is from 1 to n, so we can just simplify it like this, right? If you look at this term in the middle, right? So this in the middle is again a composition of 2 terms. One is this term times this term, summation so many times because they are the script here, okay? And you can move this thing up because this is a coefficient, right? This is an inner product, but this is a coefficient. You can move it out to the front. That's how you get this term. If you look at the other term, this is just alpha, y, and w0, right? And because there's a negation sign, this is something here. But w0, we can also take it out. It's a common coefficient. You only need to keep those L relevant stuff inside the summation, okay? This L, this L. Another thing is that I think for now, you will easily see that the vector length squared is equal to this, right? This is inner product, W1 squared plus W2 squared, W3 squared. Okay? Any question from here to here? I hope everyone's on the same page, okay? Yeah, if this is okay, let's continue, okay? The inequality constraints, okay, are incorporated into the second term, right? So this is the second term. So it's no longer necessary to enforce them explicitly. But the Lagrange multiplier, we do have to enforce this thing, okay? And here's a link that I will not go through, but you know, this is the you know, dual form, right? So the optimal solution, we can prove that when we solve the problem, right? So the optimal solution is a saddle point, which minimizes the LP, right? So we want to minimize the LP. This is you know, this is a margin, right? So this is what we want to, how to say this? So we want to maximize this, because if you remember, we just mentioned, right? So we want to maximize the margin, right? So this is equal to this, okay? So this thing is what we want to, let's say we want to minimize, right? So yeah, minimize, okay? The optimum solution is really, so we want to find the primal variables to minimize the option, okay? But the dual is to maximize. So this is kind of reverse, because the problem there in the link is talking about the maximization. Okay, we are talking about minimization, so this will be reversed. Okay. Anyway, so keep in mind that we have, in order to go through the original parameter w's, right? We need to introduce new parameter like alpha. Alpha L is a new parameter. Okay, and keep in mind how many alpha are there. There are n of them. That's the key why we can convert to the dual space. We only have n parameters. Right? These are the n parameters. Newly introduced n parameters. One for each data row. Okay? You see, the L is the Lth row of the data. Okay, for each row, each data, we have an alpha L introduced. Right? It's looking like crazy, but so later we'll see that support vectors is a very small subset of all the rows. Okay, we'll see that. Right. So the saddle point basically says, while your W's you are trying to minimize this, right? So the newly introduced you are trying to maximize. Okay. There's a theorem for that, called the saddle point theorem. Let me clear this. Another requirement I forgot to mention is that so when you, let's say you want to minimize this, right? So in the primal form, okay, and your dual form you want to maximize using alpha, okay. While doing this, you are assuming they meet at the optimal point, but there's no guarantee here, okay. So you can have a gap, and you don't reach the optimal point. So there's a requirement for you to get the optimal point called the KKT condition, right? But it's a little bit crazy for us to expound those things here. Okay, just to keep in mind what we discussed here satisfies this KKT condition, right? So let's say when you take the dual form and you do the optimization, you get the same solution as in primal form. Okay, but this is not always hold. You need to have some condition for that. All right, so let's continue. Now that we assume that then things are super simple, right? So we want to find the W and W0 and take derivative 0 set to 1, then we will find the optimal W and W0. Right? How do we do that? Let's take a look at here. So again. Firstly, if you take a derivative this, what will be the result? Who can tell me? Okay, so yeah, so this is 2W. This is W because 2 by 2 by 1. Okay, this is W. If you don't know how, there are several ways, right? So you need to follow our rules, right? So one way is saying this is projective form, but the matrix identity matrix, okay? And we know that projective form is saying that it's equal to what? It's equal to, I think it's IW plus I transpose W, right? And so this identity matrix time anything itself. Identity transpose is anything. It's a diagonal one, okay? So it's W plus W is 2W. Okay? And this there's a 1 by 2. So you cancel. This is okay? Always try to follow the rule we teach. Okay? And actually you will immediately see this rule here if you follow the definition. Right? So another way is to see the definition, because this is what? This is W1 square plus W2 square. So WD square. Right? So WD square. And now keep in mind what's a derivative, right? So it's a vector. It's a vector, okay? Where you take a derivative this to W1 first, right? So to W1 first, this is 2W, okay? And then finally you take this to WD first, this is 2W, okay? And then you divide by 2, this is 2W. So this is relative, okay? So there are different ways to see that, but you need to play with the rules that we taught in earlier, Okay.
That's a vector identity there.
What?
So
Yeah.
you have WT times, you got WT times I times W. You can split it up into those two terms. That's one of those matrix cook.
Yeah, exactly. So if you look at our previous slides, let me see where it is. Preliminaries. Again, you guys need to refresh your mind on this stuff. Right? So if you, especially the assignments, is get you familiarized with those things. Right? So, for example, now we know that we have this W square. Right? So this thing is what? W1 square plus W2 square plus WD square. Okay. Right. So now this is G. Right. So if it's a G, take a particular to W1 is 2W. Okay. take a partial derivative WB is 2W. Okay? Right, so this is really 2W. It's okay?
Yeah, that's good. That's fine.
Yeah, so another way is to use the formula we asked you guys that you have to remember. Okay, so this is first thing. So now basically we are talking about this is identity. Okay? This identity. So this identity times W and identity times. Okay? It's 2W. There are different ways because these mathematical formulas are well proved. Okay, you need to memorize them just like you memorize how XA take derivatives AX A minus 1. Right? I ask you to prove this right now. You don't know how. Right? It's taking limit. Right? It's the same. You need to memorize these things. Okay, at least those linear form and projective, okay? As we emphasize again. So the others you can go to Mixture's cookbook. But these two you should really have in your mind. Okay, and that's also what we require in the first assignment. Yeah, so I mean the first written assignment, right? So now we know that if you take partial derivative this is W, okay? And then the other term that's relative to W this term, right? And now you are using our, the other formula I asked you to memorize. If you have ATX, take partial derivative X, okay? So these are that. This is A, okay? Right, so basically, if this thing is in the product this and this, okay? Right, so you can write it like this thing transpose times W, right? And if then you look at this formula, this should be this thing, okay? So the second term is minus summation of this, okay? And we set it to 0, right? And if this is the case, basically we say W is equal to this, okay? So that's why we have this first term. The second term is take a derivative to W0, okay? When you take derivative W0, you just look at the term that contains W0, right? And you take the partial derivative W0, which is scalar, right? So it's the coefficient minus this, right? And then you set to 0, right? Which means the summation of alpha y is 0, which is the second term, okay? Any questions? Yeah, if you cannot follow, you need to watch the video. Okay, we share all the videos on YouTube. Okay, now let's look at the dual form, right? So if you remember, so the objective function is this one, right? We have the first term and we have the last term, which is here, okay? The two middle term is gone, okay? Why? Let's take a look at why, okay? First is this, remember this is 0, right? Because this is 0, this thing is 0, this term is gone, okay? And the second, actually it's not gone, by the way, my mistake. So this is negative 1/2, right? So that the other is positive. Remember this thing is W, okay? So we are just saying this thing is W, right? So if you look at these two terms, this is 1/2 W transpose W minus W transpose W, right? So this is really negative 1/2. It's okay? This is how we derive this term. Okay, and the other term with this 0 is gone, and the last one. Any questions? Yeah, I hope this is fine. And I see a lot of students are leaving. Yeah, I hope they will stay because we will take attendance. And so now, this W term, right? So it's this W term. If you pull this here, what you will have is this thing transpose this thing, right? Okay. So what will be the result, right? So it's really in the first process you take the L term, okay, which is this, and this, right? In the second term, you take the L prime term, which is this, and this. Okay, it's really how you get this. So it's a product of these processes. It's like a for loop, and this is two level for loop. Okay, and so this first term you have the transpose. So this transpose going to the vector times the other without transpose. So that's why you get kind of inner product. All right, so now if you look at here, so what does this mean? So this is the inner product of your L's. Let's say you have a data table. Okay, you have a data table. This may be your prediction. This is x1, x2. So this says that this is inner product between two terms. Okay, this is L's row, your feature, and this L prime feature. Right. So you take the inner product of these vectors. This is value for the one term. Right. So you have so many terms. Okay, summation. Right. One term have a coefficient here. Right. And this you can show that this function, this term is, this thing is a projective form. Right. So I think you can see it. So yeah, so if you look at this linear form, this quadratic form, you can write it like this. Right? You just put it. Right? We want to maximize this because it's a dual form. Right? We want to minimize W because we want to maximize margin, then we want to minimize W. And when we minimize W for the dual form, we want to maximize alpha. Okay, this is according to the theorem and the saddle point theorem. Okay, and we do have the constraint. Right? So the constraints here. We cannot drop this one. Right? We only take this one into here. This one cannot drop. Another is this constraint. Right? So because we have inequality constraint, so this term should be there. So this is our ultimate dual form. Okay, and keep in mind, this is just the two rows feature vector timed together. Right? So it's a scalar. It's an inner product of their feature vector. And then there are labels. Right? So this is a constant. Okay. This is a constant. The variable, the true variable is really this thing that we are optimized. Right? These alphas. Okay. So if you look at the quadratic form, I think maybe it's more helpful if we go to a really slide. Okay, just one moment. I think the same slide. So that we see before. Let me go to that page. Okay. Yeah, so here are the quadratic, right? So basically, we are saying that this is what? This is the alpha vector, okay? Alpha L1, alpha L2. If you have 1,000 rows, then it's 1,000, okay? And this is really the projective form, right? So the alpha L prime, okay? These are the true parameters. This is the constant, okay? In the matrix, right? So this is the function of the alphas. This is the quadratic form. Right, so basically, we have alpha transpose times some quadratic form. Let's see, right? And you also have the linear form. So you have another linear form at the beginning. Okay? And we can show that this A is positive semi-definite, right? So we'll see whether we have time to show this later. Okay, so yeah, so because of this reason, this problem is complex, and we can do the complex normalization because if this is something like this, oh, by the way, we have a negative sign, so it's a concave, right? So we can do the convex normalization to find the maximum. Okay? So this is how to connect to the previous knowledge. Okay, so basically, let me clear. So here's what we are talking about. Right? So this term, keep in mind, this is constant. Right? So this term is really alpha vector times a matrix times alpha. Okay, and this is the linear term. Okay, this is a linear term. This is alpha vector itself, right? Times one vector. Okay, one vector. Okay, so this is the inner product between 1, 1, 1, 1, and alpha. Then you get this. Right? This is the linear term. Okay? This is a quadratic term. And we can show that the quadratic term, the ij's, let's say call this I, this j. Ij's item is the matrix element is, and we can show this is a positive sum definite. This is exactly like how you show that the Hessian matrix is positive sum definite. Okay, because you see this, right? So if you write it like no xi and xj, because we would like to use ij to from this. This is easier to see. This is like what? This is like auto product, right? That's the beginning point of how we would prove that the Hessian matrix is convex. Okay, Hessian matrix PSD, positive sum definite. The only difference now is that they are no longer scalars; they are vectors. Okay, when you have vectors, it's a summation over the element ones, right? So that's why. So there's actually an additional level there. Okay, so it's like a A1 plus A2 plus A3. You can show. It's very similar to how we prove the Hessian matrix positive sum definite in our in our assignment. Right, the previous video we talked about in the beginning of this course. Okay, you can show that the A matrix represented by these things for the ijth item. This is the ijth item, this value. Then if you look at the A matrix like this, okay, this is a positive sum definite. Okay, because this quadratic term is something like this, right? Ax squared. Okay, this is A, this is x squared, something like this. Then you have the negative sign, this becomes this, and that's why it's convex. It's concave, you can maximize this, right? So this is basically why then you can use a QP solver to solve. But if this term is not positive semi-definite, it's not a convex problem, you cannot use it. Okay. First, it's a quadratic term. So this is a quadratic target function, and this is the linear constraint. But again, this target function is convex. Now you can solve it. Okay, you can find a QP solver to solve it. And a few more notes. So you may ask why we want the W squared, right? So that's exactly for derivation purpose. Okay, so if you look at here, because the target function is W squared, right? So when we have the W squared, right? So then when we take a derivative, we have this term. Okay, we have this term, and when we come back, we have this term. Okay, then it becomes QP. This is exactly why we need to minimize W squared. Minimize W squared, not minimize W itself. Okay? If you minimize W itself, you will see it doesn't work out when you take partial derivative. Okay? You can try yourself. And the nice thing here, what's the nice thing? Right. So the nice thing here is this is alpha vector is of size n, because one row in your sample data you have a one alpha L. Okay. Right. So you have altogether n alpha L you want to optimize. Right. All these things are constant. It's given your data matrix, right? So the computation are all relative to n. There's nothing related to d anymore. Okay, right? So d are already, you can pre-compute them and make them constant, right? And again, there's a complication here we didn't mention, right? What if the d dimension is infinite, right? We will see how to handle this later. So basically, we can use a kernel function to compute this without going to the infinite element dot product. Okay, we'll see that. We can compute a simplified function. But this is not always true for any mapping from low dimensional space to high dimensional or infinite dimensional space. Okay, that's only for particular kind of features, mappings. Okay, but those works well. That's the foundation of SVM. Okay. Let me see how many we still have left, and then we take a break. Okay, let's finish these few slides. Okay. Yeah, so the concept is support vectors, right? So for this optimization problem, what you will find is that because we are computing alpha L, right? For one row you have alpha L. Most of these alpha L's will vanish, which means they will be equal to 0. Keep in mind, they cannot be negative, okay? They can at most be 0, right? They will be 0. Why? These points are lying on the margin and lying beyond the margin and had no effect on having. So from optimization point of view, it's not so easy to see, but if you look at our previous, let me see. Let's get the intuition directly from our from this diagram here. Okay. So you think about it. Even though you have a lot of points, right? Even if you add more points here, right? You have another row. They do not change the shape of this hyperplane. Okay. So only thing that decides the hyperplane are those points that are on the boundary here, right? Let's say if you add another point which is here, then your hyperplane margin is moving here. Okay. Beyond these two lines, you can add any point. There's no impact, which means the associated weight of L is 0. There's no impact on the shape. Okay. Only these things, their weights play a part in deciding the shape. Okay. So this is intuition that helps you understand why most alpha are good. Okay. Keep in mind, one row, one data point is associated with alpha because we are in the dual space. Let's see. Okay. So associated with these alphas, right? So if an alpha is let's say positive, right? Most of them are 0, but some of them are positive. So on the boundaries, right? Their associated data points are called support vectors, right? So keep in mind, support vectors are no more than just the training data points, right? But they are a subset of them that is selected using optimization. Okay? And that's why we call it a support vector machine, because using those data point vectors, right, you can define the hyperplane. You don't need all the points. Okay? So the support vector machine is very space efficient when you save the model. Okay? And another thing is that we really want a simple model, right? So you don't want too many support vectors. Okay? And because there's a learning theory saying that the number of support vectors upper bounds the error. Right? If you have a lot of support vectors, that means your error could be larger. Okay, could be larger. So if the less you have, the less your test error will be. When you talk about test error, it means after training how you generalize. So the less support vectors you have, the better generalizability. Okay. Analogy is that you can think about the polynomial fitting, right? Polynomial function fitting. Okay. If you use order 9, it's going to overfit. It does not generalize. As if you use small order, it's the same. If you have not too many support vectors, it works well. If you have lots of support vectors, actually it's not good. Okay? It may be good on your training data, but not on the test data. And finally, let's put things together, right? So keep in mind what we are actually predicting in our model, right? So what we are predicting is we want to train the model, right? And once we train the model, we want to put another row that has never been seen here, right? And we want to get its y. Okay, what's the given x, what's y? Because we are considering classification in this lecture. Okay, we'll talk about how to do the regression later. Okay, so in order to do that, right? So what we need is, firstly, after optimization, let's say we already have those alphas, right? And we also know there are labels and there are vectors, that's a feature vectors. Then we can compute W in this way, right? We can compute W in this way. And actually, we don't need to compute W in this way because, we only need to look at the support vectors. It's like you have a set of support vectors, you just do for loop on them. Right? The others, you can do for loop and compute them, but because their alpha L is 0, right? They don't play a void key. So you can actually just compute from a small subset of those X. And if you want to compute those points lying on the margin, right? So those support vectors are exactly those points lying on the margin. Okay. Once you put those support vectors value in there, this is exactly one, right? Remember, we want a larger equal to 1. But if they are exactly on the margin, they are support vectors. This is equal to 1. Okay. What does this mean? Right. This means this. Okay. We can show this. I hope you can see why. If not, let's do a derivation. But I think it's very crazy, too many marks. So here you can do something like this, right? You time YL on both sides, okay? This becomes YL squared. YL squared is always 1, okay? No matter your Y is 1 or -1, YL squared is always. So this term is gone. Right? So So now you have this plus W0 equals Y. So W0 is YL minus this. Okay, then minus this. So this is how we get this. All right, so now what does this mean? Right, so when you compute W, you do need all those support vectors. Okay, but when you compute W0, right, you compute W0, you don't need all the support vectors. You can use any support vector that are on this line. Okay, you will get W0. But there's a problem, right? So because our computers have a limited bits, right, for each number, like 64 bits, 32 bits, right? But your number could be having actually more precision, right, like pi. You cannot represent accurately using just a limited precision number. Okay, right? So there will be some numerical errors here, right? So for each support vectors, it may introduce some error to W, right? So you want to cancel out those errors by considering all the support vectors. So basically what we actually do is, so this is the estimator of W, right? But each support vector will give an estimator. We will take that error. So this will reduce the error, right? So as we said, if you have one data, the error of one thing, the variance is the variance, right? If you have 10 support vectors, the ultimate variance will be variance divided by 10. So it's more stable, right? So this is how, based on, let me clear this. Let's go to the next. This is exactly how, so first you do optimization, compute with alpha, okay? And then these data are already given, right? So based on these data given, you will get W, and based on these data given, you will get W0, okay? It seems that W0 doesn't depend on alpha. No, it depends, because these are the support vectors, which are alpha is not equal to, not larger than 0, okay? Equal to 0, right? So first, do the QP, get the alpha, and using alpha and using the existing data table, you will get W in the W0, right? And once you get this W and you get this W0, right? So this is what scikit-learn or libSVM is doing for you, right? And you get the discrete function. Remember, our discrete function is again still the same. It's a line, right? On this side it's 0, it's a positive. On this side it's negative. Right? We just want some margin to make sure nothing is in between. Right? So the line is still that way. And so it's still this. Right. Once you computed these two weights, right? So you get this line. And for a new data item you see, you just pull it here, and then you see the GX value. Right? It's positive, then you are positive class. It's negative, you are negative. But unfortunately, support vector machine is always for two-class classification, right? So how do you handle k-class classification, right? So we will see that later. Okay. So we will use the two-class classification as a model, and we will generalize to k-class classification. I think we will take a small break and then we'll come back and we'll take attendance. Okay. In the meanwhile, I think some student has a question, right? So earlier, and because of the signal issue, cannot ask, right? So I will be here. Let's come back in 6:40. Okay, so then we come back. Right. So in the meanwhile, if you have a question, feel free to ask. Okay. Any questions? Pruvi, I remember you have some questions regarding the math testing. Feel free to ask me if you want.
I have a question about the homework.
Okay.
So we have to, I think, use the Newton method, and I'm kind of lost. Are we supposed to have to do some dimensional reduction or something like that first?
No, you
before
don't
we do it, or
you don't have to do any dimensional reduction. You use the original dimension. I think the data has maybe 10 dimension or less, right? So that's
but
yeah.
Right.
Yeah, it's at most 10 by 10 matrix for the Haitian, right? It's not big. Okay.
Yeah, because in the example, we have let's say just like the scatter plot version, which is basically 2-dimension, and but for I don't know if 10 dimension it's going to work differently or not.
Oh, it's the same. All our all that we presented here, like Newton method, derivative, they scale to any dimension. Right. So these are high dimensional multivariate calculus. Yeah. So we don't tell you why, because if you want to do that, you need to learn the complex normalization, multivariate calculus, etc. But these conclusions are true. Okay. So we are trying to familiarize with you guys with those conclusions so that you can use them. Right.
Professor.
Yes.
So the data I noticed, it has 11 columns. So, but the first one is just image ID, and the last one are just labels. So we should just work with 9 columns, right? That's how I interpreted it, because I don't think the ID image
Which
or the
data are you talking about?
Wisconsin data, the breast cancer data set for the assignment.
We only have 2
That's all.
classes, right? So 2 and 4. 2 you map to the public class 1.
Yeah, I understand. I said that there are like 11 columns, but out of that, I feel like that there are 9 features that are only useful. The first
Yeah.
one of the features is just
ID
data
column,
ID.
you need to drop it. Right? So
Yeah,
apparently
that's
ID
what I
doesn't
said.
matter. Right? Yeah. So you need to do some pre-processing. We don't get all the details. You do what
Oh,
you
no,
see.
I did that. Just wanted to verify. Yeah, so I
Right.
dropped that. Yeah.
So you just think about ID. How can ID decide your label? Right? So it's kind of random.
Right, exactly. Yeah, so that's why I dropped it. Yeah.
Hey, Professor, I'm sorry. Am I audible enough?
Yeah.
This is.
Yeah.
So yeah, I'm so sorry. I mean, I'm having a lot of technical issue at my home. It seems. Okay. Yeah.
I see. Yeah. Please go ahead. Yeah.
So yeah, I did the same thing. Like I've selected this TensorFlow version 1.x. Yeah, I was able to do that. So the code which you gave us is only for the validation. No, I don't think it's not written for training, right?
Yeah. So basically, here's what you need to do. So because I see Latif shared this link, I know what's intention, so I just opened this. Okay. Maybe show you how to do the TensorFlow run. Okay. So basically, there's some magic function in JavaScript, right? So or
yes,
to the notebook, right? So maybe one is a magic function, 2 is JavaScript, and a exclamation mark is for shell, right? So the Linux shell, and without it, it's pure Python. Right? So and so let me see. Yeah. So actually, you can do something like this. So if you look at Mask.cn, I think it's from Matterport. It's TensorFlow. So there's also Python.
Yeah,
So,
I read the.
So what you need to do is this, right? So you download, so the first thing you play with the library is look at the instructions, right? So clone this repository and install the requirements because they have some packages that you may be missing, okay? You run these requirements. You look at the requirements, it's a bunch of package names. It will help you install, okay? And then you run they have a script to help you install those things. They're called setup.py. You need to run these things, okay? And then this is a pre-trained way to download and you will be able to use it. So the only difference is that here, they only work for TensorFlow 1, right? So if you want to use TensorFlow 2, you need to replace this model.py after you install these things with TensorFlow model.py that we provided in our test data. The one that we provided.
Yeah, I mean, I'll do that. I understood, Professor.
Yeah. If you didn't install, then it will not work out. Right? So because they ask you to install. Right? So put simply, what it does is this. Right? So let's look at requirements. Right? It's a bunch of packages. That's SciPy, etc. Right? So they need you to install.
There's one more problem as well, Professor. So the default Python version is also different. That is offered by Colab.
Colab is you mean it's different?
Yeah, even when I'm installing, when I'm trying to create the Anaconda environment, there is no 3.4. I think it's depreciated, but as per Matterport, they need 3.4 of Python.
You can change your run type. You can have TPU, GPU, and you can. Let me see. I think there's a setting there. I don't remember the details, but you can choose to use which version of Python. I believe. Let me see. Runtime. Tools, settings. Yeah, unfortunately for this course, we do not have too much time to cover the coding part, right? So because the time is very limited. We spend all the time tell you how to use tools, and we don't have time to cover the lecture. So but we have the high level pictures, and you can go and delve down into the details. Otherwise, if you don't have the big picture, we give you a bunch of details. That's not helpful. Right? So you still get lost when you use details. You just remember those small details, but you don't have the big picture. I think there should be some configurations. This is support. Let me see. So you can Google, for example, you want to use Colab. So your Python version, you can change. Right? So basically everything can be Googled once you have the big picture. Right? So for example, you want to change from one version to the other version of the solution. But anyway, so the Google gives you the virtual machine. So you can freely version. Yes, there are steps. Okay, there are steps how you do. So basically, you are on the virtual machine. You just say, hey, the virtual machine, I want to use that Python code. Okay, there are some ways to do that. For example, let me just try to see whether this will be made work. Okay. Let's go to Colab and take a look at it. I remember Latif sent a link which leads up to Colab. So let's just create a new Colab. Colab. So we create a new one. Okay, so okay, so let's connect allocating a machine. So let's run something. Add a code, and let's see. Python version. How do we do that? Version. Maybe this one. I don't know. Let's
no. I think Python hyphen version.
What?
And with a semicolon in the start, professor. Semicolon.
Semicolon. This?
Not the semicolon. Exclamation mark at the before Python.
Yeah. It's a Linux. So yeah, this Python version. Yeah. You want to downplay it to. Basically, you can see how
3.4. As per Matterport, it's 3.4.
3.4, right? So
yeah.
Change Python version. I think this is basically Linux stuff because you are now on Linux, right? So in Colab, everything you can do, like you can look at your disk structure, sample data, and you can look at. So basically, it's your virtual machine. It's just how you reinstall or change your it's once you connect, it's a virtual machine assigned to you. Okay. The reason you are using that Python version, you see the RAM and the disk, right? So the reason you are using that Python version is simply because it's a library installed on that Linux machine using this Python. You can run command, how to downplay the Python version you can change. Okay, so let me see. Change Python version of down. But again, if we spend time on this, then we will have to compromise a little bit. So for example, this blue, so Kunda install. I think the simplest way is just to say, so which version do you want to install, by the way?
3.4. I mean, I'm just following the recommended one provided by Matterport.
Yeah, if you want to uninstall Python, for example, we can first uninstall Python. So it's not installed. So
yeah, even Colab is not letting to do that because I mean, the whole Jupyter notebook needs to have Python. I already researched about it.
So I see they have a lot of restrictions. You cannot change it directly also. So what's the version you want to install? Let's try this.
As per the mat report, it's 3.4.
3.4. Let's try this. Equal.
Double equals to.
Maybe we should add 0. Cannot find the version. That's after a requirement.
Yes, I mean, if you see the mat report medium channel, I mean, medium page, it's clearly mentioned as, I mean, they're very specific about that.
But I don't think it's a
That's
Python
right.
version. You have to downplay the Python 3 are all the same. Why you have to use 3.4? What's the difference from 3.4?
I mean, it's actually mentioned in mentioned by them, like Python 3.4,
yeah, exactly. So this
TensorFlow
requirement
1.3.
actually is a minimum requirement. It's a minimum requirement.
Okay.
If you look at the requirement here,
So if I just interject, so the,
yeah, it's larger than equal.
when I,
Right. Yeah. Some of you say.
yeah, so when I ran the mass-car CNN codes, I ran it on 3.7 and it worked fine.
Yeah, basically it's
The
it's larger
environment
than
that
equal to 3.4. Okay. If you have an upper version, it's fine. Do make sure you install it, right? You need to set up so that they install anything that was missing here. Okay.
So yeah,
I don't know why.
Then,
Yeah.
Python version shouldn't be older version, 3.7 or higher version shouldn't be an issue with Python.
Yeah. This is also what
I mean,
anyway, you can play with it because of the limitation. Maybe you can talk to the TA in the TA hours, okay, and they will figure out what's the problem. I don't think it's a Python problem.
I mean, it's not just the that version problem, Professor. Like, it's everything is independent. Like, I've tried TensorFlow with 2.0 and it was not working, so I downgraded it to 1.14, which is also not working. So I had to stick to 1.15.2.
Yeah, if you stick to that, then works. Then just stick to that. Right. So another option is you use our, as I said, if you use TensorFlow 2, you change the model of pi using our model of pi. That will work. Okay. Yeah.
Okay.
I tested.
Yep.
Okay? Yeah, that's how I make it working in the new version. Okay. So we already make it work. Right? So just change the model of pi if you use TensorFlow 2. Otherwise, you downgrade to TensorFlow 1. Both of them. Yeah, I think we need to continue because it's already 5 more minutes past. Okay. All right, so if we want to generalize to k larger than 2 classes, keep in mind that SVM always is that linear plane, which is separated into space, right? It's always positive magnitude, right? So if you want to really, you want to really k classes, what you can do is this, right? So you can have a 2-class classification problem. So basically, this is what you do, right? So you have class 1, and you then SVM differential 1 with 2, 3, right? Differential 2 with 1, 3, okay? Differential 3 with 1, 2, okay? And then you for each of them you have a score, okay? And then let's say for this score is 10, this score is 20, this is 30, right? So if this guy is the highest, then you take class 3. But this is just a way to make binary classifiers work with k classes. And we have seen also another way, right? So you can do pairwise comparison. So this is all we covered in earlier course, earlier class lecture. So for k classes, you can do this. Right. And I think scikit-learn, the SVC already handled this for you. It's already k class. Now, the previously described support automatic machine is not sufficient, okay? Because we assume the 2 sets of lines are separable. But there are a lot of reasons that makes it not practical in practice, right? So in reality, we never use that thing we described because it will not work, okay? Because, a separate hyperplane may never exist, right? So when we derive this, we assume there's a hyperplane with some margin to both the positive and negative points. But what if they are mixed together? Right? There's a high level of noise, right? So in that case, we cannot find such a, right? So let's say you have, let me see why. Oh. Yeah, this is, yeah. let's say you have a bunch of negative points here, right? And you have a bunch of positive points here. Okay. And what if, let's say, on the boundary of it, right? So you have a point, some noise, okay? And you also have some negative, right? So you cannot even draw this line, right? When you cannot draw this line, our previous derivation doesn't make sense, right? All our previous derivation first assumes you can draw a line that separates both and with some margin, right? So if you have a high noise level, especially when in the boundary that mix, then you cannot find such a line, okay? There could be overlaps of the positive negative in a small region in the middle, okay? So another reason is that there may be, there's outliers in the data. Okay, so maybe somehow this negative sign is here, although it's very unlikely that it's an outlier. Another case is really, mislabeled data or some noise in data. So noise means, when we talk about noise, it means that your x1, x2 shift to the other side. Okay, when we talk about mislabel, it means actually this is negative, right? So you mislabel as positive, right? So that's also negative, right? So you both noise and mislabel will cause your data to be inseparable, right? Which means if you, let's say you originally your data is separable, okay, negative, and suddenly you have a mislabel, someone mislabeled it for you, right? So then the whole thing doesn't work, okay? Right, so this is not good. We want a more robust classifier, okay? And the way to do that is, now previously we assumed that we need to have a margin of 1, okay? Now, what if this cannot be true, right? So this could be 0.6, which is still positive, right? So it's still correct, right? But this could be negative 20, this is very negative, right? So for this, basically we allow it to have some slack variable, okay? So for example, if you have negative 20, we just say, hey, the slack variable is we set it to 22. 1 minus 22 is negative 21. Okay, so this negative 20 is still larger than negative. So as long as we make this large, we will always be able to make this condition satisfied. But we pay a cost that there's some shift, which is not desirable here. So here we will introduce those slack variables. Okay, so remember this is L is for each row of the data. So for each row, we have slack variable, which means for this data row, maybe it is not satisfying this requirement by a certain amount. By certain amount. Okay, for each row we have this relaxed separation constraint. And in this way now, actually, at least we can draw this line because even this line is not satisfying the requirement. We can increase this variable to make it satisfy. Okay. Any questions? Okay, if not, let's continue. Right. So we can just make this variable large enough. Okay, then the constraint can always be met. So then now we don't have the issue that we cannot draw a line. It's just as which line we can draw so that this thing is not too big. Right? When it's big, it's not so big. Right? This now becomes part of the optimization variable. Okay. And if it is big, we definitely want to penalize it, but we want to add some penalization. Right? So as a summary, what are we having here? Right? So remember, we want to be larger than equal to 1 minus this. Right? Okay. So if this thing is 0, which means you have no problem. Okay. So if you want a margin, this 0, this 1. Right? Okay. If you don't need any slack variable, which means you are on this side, that's fine. Okay. And if you are in between 0 and 1, that means this thing is still larger than 0. Right? So on the right side of the thing, you are still positive. Okay. But what if this is larger than 1? Okay. Then this thing becomes something negative, right? Negative 21. Then you are on the wrong side. Okay. It's a misclassification, right? So this should be large penalty. This should be a small penalty, right? Because we want a margin of 1, but you're within the margin, so you are still correct. But when you go to the other side, that's wrong. Okay. Any questions? Yeah. So let me clear this. And so again, so number misclassification is if this variable is larger than 1, then you have misclassification. right? So a number of non-separable cases, which means it could be misclassified, but it could also be just in the margin. Right? If it's in the margin, then it's it's on the right side, right? But it's in the margin, then this is a non-separable case. Okay? So this case includes it. Okay, it's just not on both sides of the margin. And we do need to penalize, right? So keep in mind, right? So although we need a large penalty, right? This penalty is already contained in this variable, right? Because this variable is larger than 1. Here we give a small penalty because this variable is smaller than 1. So we can just use this variable as a penalty. Okay. For each row, we have a slack. Okay, slack. Now for all the rows, how much total slack we have? Right? So this is a slack. This is the undesirable slacks that we have to put in order to make all our data satisfy this requirement. Right? We add some slack so that it's not funny. So we want to minimize. So we want to minimize this penalty term. Okay. So because we want to minimize this penalty term, so we want to add this thing here. Right. So then we minimize this. Okay. Right? Because we originally want to minimize W, because we want to maximize margin. Right? Now additionally, we also want to minimize this signal. So this is all minimization. Right. This is where we come with this term. If you ask for this term, right? So where does this thing come from? Okay, this is because now your constraint when you do the Lagrange multiply, this thing is moved to the left, right? So you have another variable here. So just like how we derived things before, but now we have additional variable when we do the multiply. And finally, we have a constraint like this, right? This constraint is newly introduced because we have this requirement. Okay, so let me see. We have this one. Slack variable should be larger than or equal to 0. For why? Let's say this is a 0 line. Okay, this is a 1 line. Right? So if you are here, right, you are here at this point. Okay, then of course we want to minus 0.5 so that this is larger than or equal to 0.5, which is satisfying. Okay? But if you are here, right? If you are here, of course we can say you can add 1. Okay, add 1. This is 2, right? So add 1 means this is minus. So you can use minus 1. But that doesn't make sense. Right, so you don't need that. As long as it's larger than 0, than 1, you can set to 0. Okay? So no point to make it smaller than 0. Okay, so no point to do that. Right. So that's why. So this thing should be always larger than or equal to 0. Right? If you use a Lagrange requirement, this is where you have this term. Right? So this is larger than 0. Because this constraint is on the left-hand side is this term. So then you have Lagrange. This is execute this constraint. This constraint. Okay. Any questions? By the way, of course you can make it a negative value, right? So making a negative value seemingly will reduce the penalty, right? But you think about it. Making a negative value will also change the W's, okay? Right, so you shift this line a little bit, okay? So that makes this a trade-off. Actually, there's no sense to make it negative. Okay? This is slack variable, which means how much loose relaxation you have. It's always a part. And this term is called a regularization term because just like lambda for L2, L1 regulation, right? This penalty term. How important this penalty term is with regard to this term, okay? This original target function, right? So these notations are actually quite descriptive. If you look at, so maybe by default you are using this library, but this C is exactly the C, okay? As we look at the explanation here, this is a regulation term. So if you don't, if we spend all the time giving you examples of support vector machine, you don't even know what is C, okay? You spend more time on mathematics, and when you come back, you know how to stack those things. So you are more advanced user of second. Okay. Any questions? So again, so this C trade-offs the model complexity. You need to use, let's say, greater search, right? So the greater cross-validation in scikit-learn to find the best C, okay? Right, this is model complexity, hyperparameter, okay? The larger, of course, the simpler model, right? But this may cause data misfit. It's just like what we see in the very first lecture, okay? And both the misclassified instances and the ones that are in the margin are also parallel, right? Because we really want our data to be on the other side of the margin, right? So at least distance 1 from the boundary, okay? Even that you are in the right side, but if you are within the margin, you're also penalized. Okay, so the dual form of this thing has a dual form, right? So this term looking exactly like before, right? Who can see the difference here? Anyone can see the difference from our previous derivation? Let me go to the previous derivation. Okay. It's 23. So let me go. So this is 13. Okay, this is our previous derivation. Okay, from the gradient, this kind of stuff. Okay, do this and this. Right? Now we add the slack variable. It seems that it's almost the same. So yeah, what's the difference? Who can see the difference? Yeah, so only difference here, okay? Because we introduced the C, we have emphasized C, right? Okay. This is a new introduction. Okay, so this is the only difference here, right? And so the derivation is still like before. Okay, so just because we have something new, but let's go through this derivation here. Okay. Yeah, just say some typing in the slide. Basically, they are showing that, for example, primal dual. So exactly like before. Okay. Now we add this value. Its dual form is alpha quadratic. Okay. And so what they are doing is this. So now that you have this term, like before, we take a derivative W. Okay. We take a derivative W. This thing is W. Okay. And this term is this term, right? Because of this is the inner product. This is order 1, right? So the linear partial derivative. This is a quadratic term. Okay. So you should remember these two. And all we require to run these two, and you will be able to do assignment. And a lot of machine learning literature. Okay? And so if you take a derivative W0, which here we use B, okay? And then you get this, right? And the only difference now we have C. Okay, we have C here. But C is a constant, it's hyperparameter. We have the newly introduced slack variable that we use to take the derivative, right? When we take the derivative, particular variable here for a particular R, this is a C term. Okay? And in this term, we also have this, this variable here, right? And associated alpha i's with negation sign, we'll get this. Okay. And finally, we have this term, right? For this sigma I, we have this coefficient is negative. So we have this. So these are the partial derivative, right? So because we have the new slack variable, so we have another equation here. Okay. And so there's no change for W and W0. Right. The only difference is here we have this term. And keep in mind, this thing is larger than or equal to 0. Right. So why? Let me see. Because this is the constraint, right? This constraint is not equality constraint. This is inequality constraint. Okay. This is inequality constraint. Then our Lagrange variable should be, larger than 0 because this is the inequality constraint. This Lagrange variable should be larger. It's it's just like what we described before. Like the alpha I should be. So this alpha I is actually already including our previous restriction, right? But this beta I is a new interaction. But we don't really want a beta I. Okay? Beta I is difficult to cope with, right? So we finally will eliminate beta I. Okay, a limited beta. Okay. So in order to do that, right? So we just use let me see. We just use this compute. Right? So we start that this thing should equal to 0. Right? This partial which is this. Okay. What does this mean? This means C minus alpha I is equal to beta I. Okay. And we know that beta I is larger than 0. And then we can just eliminate this. Don't look at this. Right? So this basically says alpha I should be less than this. Right? So this is the only new introduction when you take partial derivative. Right? Any questions? Yeah, so these things are everywhere here and there. Right? So maybe you previously you learned the support vacuum machine, and they will not go such depths. Right? So for example, this term is really the projected term. Okay, so it's really this term, a projected line. Okay, and this term, linear term, is really this term. Okay, and we have this constraint with this additional term. Okay, and actually, if you go deeper, right, so it's there. Okay, these things are here. So it really depends on how deep you want to go. If you look at those simple courses, they just teach you how you get a G over, go through these things, and you remember, and finally you forget what you see. So we are trying to get you the big idea, high level. Okay, then you will never forget. It's just that you may not know how to go to the library and you can go and look at the API, right? So that's what we have. And this is, again, an inequality constraint, right? So you can think about these as two inequality constraints. And these are the linear constraints on the variable alpha. So this can still using the quadratic solver. Okay? This is the quadratic constraint. This is the linear quality constraint. This is two linear inequality constraint. So you can break them into two. One is alpha L larger than or equal to 0. Another is alpha L less than or equal to C. Okay? And similar to the hard margin case, you will be able to get the conclusion that most of the alpha are 0. They will vanish. Only a few of them will be, support vectors. But again, these support vectors will be a lot more than before, right? So you look at the previous example. Let me see where it is. You may feel, what's the probability that these 4 points are all lying on this, right? So most of the time, maybe there's only on 1 point, right? So that is closest, right? So in that case, if that's so regular cases, most of the time, only 1 point will hit those lines. Okay. The real case that we will have a small number of points hit those lines is really when you allow some slack variables, right? So if you allow some slack variables, then it's slacking, so you have more support vectors. But that number is still going to be really small, okay? Compared with the entire data set. So these previous derivations still hold because the W and the W0 is still there. Right? So remember we compute alpha L using complex optimization. Right? So basically the only difference is we have an additional constraint. And then we get those alpha, we can get W and the W0, right? And then we can use it to get the linear function that we can do classification or regression. Okay. Here we are focused on classification. Regression is kind of similar. So yeah, so let's see. So basically besides SVCC means classification. Right? So if you have R, you have the regression. Okay. Again, those concepts are still here. You have the C, and you have the RB kernel and other things. Right. The only difference they have an epsilon. We will talk about it later. Okay. Okay, so let's take attendance. Right, and let's continue with kernel extensions. again, we will be sampling some students. So taking the whole class will be too time consuming and waste you a lot of time. Let's try to. Suman? Suman, are you here? No. Christopher. Christopher Coffey, are you here? No. Revent. Revent, are you here? Just want to make sure. So everyone can hear me, right? Can anyone?
Yes.
Yes.
Yeah, that's kind of crazy, right? So the probability really low because we have 3 students. Not. You know, given this attendance, this number. Oh, yeah. I think this time we hit those students that are really missing. Okay, so. Boniface?
I'm here.
Okay. And Clark Run?
Here.
Okay. And let me say, Ahmad. Ahmad? Okay, so Ahmad is not responding. And Annie?
I'm here.
Okay. And Kawan?
I'm here.
Kawan?
I'm here.
Okay. Just want to make sure. Hua Shuai?
I'm here.
Okay. And Manoj? Maybe I pronounced wrong. Okay, Manoj? If I'm pronounced wrong, just correct me. Okay, so okay, I see you in the chat. So let me go to the second part. Okay. Connor?
Here.
Okay. And Umar?
Yeah, I'm here.
Okay. Nikhil? Nikhil? No. Let me see. Ryan? Ryan? No. Okay. So we will stop here. Okay, we will go to the PhD student. Let me see. Isan?
Yes, I'm here.
Okay. Chad?
I'm here.
Okay, good. So let's continue that. All right. So yeah. So I see a student left, right? So don't leave. Okay. So the kernel part is really important. Right? So if you want to understand the SVM, right, so you need to understand the kernel, okay? Because by default, so you use kernel, right? It's not a linear. So instead of defining a nonlinear model, right, so in the original space, because right now we are defining a linear model in the original space. That's too simple. Right? So if you want to define nonlinear model, that can be more complicated. Right? So just like what we talked about, let's say a circle, right? So and a rectangle with a car engine within the rectangle, quality outside the rectangle is negative. It comes right. So then you cannot use a lot, right? So you do need a nonlinear model to capture more complex cases, right? And you can either do nonlinear model in the original space, that would be super complicated, right? Support that machine is using the other idea, okay? The problem is back to a new feature space by performing nonlinear transformation, okay? Basically, it's using a linear model, but the features, there's a nonlinear transformation, okay? So model is linear. Feature, you do a nonlinear transformation of the feature to get another set of features, right? So those transformations are called the basis functions that we see before, okay? A linear model is applied on the transformed features, okay? And the basis functions are defined implicitly using kernel functions, okay? So basically, this is what we say, right? So you cannot choose how we define features, right? So maybe you want to say, hey, x, sine x, cosine x1, sine x2, or something like this, and x3 square. You cannot choose. So once you define those kernels, these kernels will define those features, okay, how you transform them. So you have no choice on what are the features, right? So a particular kernel defines the new space, what are the basis functions, okay? The reason for that is because only these functions you can compute efficiently, okay? Because otherwise, the inner product is going to be super expensive. We will look at that, okay? So here are the concept of basis functions, right? So you have original feature space. Instead of directly do a linear function original feature space, you have defined a new set of feature space, Z1, Z2, Z3, etc. Okay, where each of Z is the function of the original feature space, x1, x2, x2, right? And it's written like this. And then what you do is you define your support vector machine as a linear function, but it's over the Z, right? So the new feature space, not the original S, right? And this data, as we said, it's this thing, right? This thing is a vector of this thing. Okay, so this is inner product. We can write it out like each say J, right? For example, the J's transformed feature is weighted by WJ. Okay, and so we do not use a separate W0 here. Okay, because we can plus W0 or we say plus B, but that's kind of notationally it's not so adequate. What we will do is we'll always define, let's say phi 1. X, okay? It's always equal to 1, right? So then this is a bias term because whatever W0 times maybe equal to phi 0, okay? Times this. Okay? It's a bias term. Right? So it doesn't depend on X. You always consider 1. Okay, so this is you can construct additional features so that you can get rid of the bias. It's just a notation. There's no difference. I think I use a wrong tool, so wow. So it's not letting me move. Just let me see. Okay. So can you see my screen?
Yes.
Okay. Yeah. So I don't know why this software has some issue. Okay. Yeah. So here's what we are doing, and usually, as we said, after the transformation, right? So this guy is from D dimension. We want to transform into a new vector. This is a K dimension. K is really huge. Right? I will say K can go to infinite. Okay? And so then this is infinite. Right? This is infinite. You will compute this forever if you directly compute it. Okay, so that's why we need a kernel function. Right? So the dual form is preferred because now instead of using the K dimension, right? Original D now is K. Okay, we actually have the alpha, which only depends on n. Right? It's not infinite anymore. It's just the n, maybe 1,000 data or 10,000 data. That's accepted. Original primal form depends on K. After you transform, if K is infinite, then you will never end computing an inner product. Okay. All right, so let's go back to what we have before. Right, so this is what we have after slacking. So we have the C here. Okay, and we just let me see what's the difference. Oh yeah, so this is different. Okay. Remember previously we have the two, we have XL inner product with X. Yeah. Now we are in a new space, right? So basically we say this is ZL times ZL. Okay. But this Z is a function of X. Okay. But again, so we will have a trouble if this Z is infinite dimension. Okay. Let's just think about extreme case. Right? This is an inner product between two infinite dimension vectors. That's crazy, right? You are writing for a loop that never ends. Okay. So elegantly mathematically you can prove for certain kind of transformation function for this file. Okay, you can simply compute this inner product using a function that is easy to compute, very efficient, right? So such functions are called kernel functions. Right. So there are other different names. Right? So for very large vector inner product, you can simply compute them using simple kernel function. Keep in mind, these are the transformed k-dimensional vector. A kernel function on the d dimension, which usually is very small. Okay. And so kernel function is also called the positive definite kernel. So you know the projective form is positive definite. Right? So as we said, something like this. Because the negation sign it will be. But if you only look at this, these values, it's positive definite. Okay, so that's why it's called a positive definite, as we explained before. And this is also the Mercer kernel, which is very often used. Okay, because later we will see another kind of kernel called the kernel density estimation. That's totally different kernel function. Okay, that's a different concept. It's not for the inner product computation. Okay, and this is also called reproducing kernel. So they are all referring to the same thing. Okay, we just call it kernel function. Right. So keep in mind. So you know this is just for the ith row and the jth row, right? So if you think about the ith row and the jth row together for different pair of rows, right? So this gives you a whole matrix, n by n matrix. Okay. This matrix is called a kernel matrix, and more often you will see it using another name called a gram matrix. Okay. It's just the matrix pairwise of the row vector after transformation taking in the product. Okay. So this is called the gram matrix. And the gram matrix is just like a covariant matrix. Gram matrix is symmetric, right? So because in the product, right, I and the j are the same, okay? And it's a positive sum definite, okay? Because this is exactly the, you know, this is exactly the alpha term. So this is the thing in the middle, okay? The only difference is that we have some constant. Why is it? So, but the y's don't impact the. You can show that you can just merge the y into the thing. It's still part of something, right? Okay, so let's look at the solution. So based on the previous derivation, right? So if you treat your new feature as z, you know that w is equal to what? Alpha y z previously. Okay, and now this z is phi x. Right? So it's a transformation of the original row of your features. Okay, and the discriminant function is a linear function, right? So if you remember, discriminant function, you have x, right? So first thing you transform into a new z space, and then on the new z space, it's just a linear hyperplane. Okay, that's w function. We just dumped the w z, so we talked about one. Okay, and the key observation here is that this w, right? This w is equal to this thing, right? And when you have transpose, you know, only this term is vector. These are the constants. Then scalar. Transpose this, right? And if you do this, basically you time this with phi x. Right. So what you have is a transform space in the product with the two rows. Okay. Right. So this x is a new training testing data. Okay. This is testing data. Right. Okay. This is a support vector. Okay. So this basically finally gives you something like this, because you know these two terms can be computed in kernel function. Right. So this is when you do the testing. Here we are talking about after you train this model. Okay. When you do the testing, you still need the kernel function, right? Otherwise, you are still computing the very high dimensional inner product. Okay. This is on the d dimension. This is on the k dimension. Right. So the kernel function is used everywhere. Right. Once you decide the kernel function. Just one moment. I see a chat. Okay. So I think one student attendance need to fix. Okay, let's continue. I will fix on the other side of my hand. Here, let's take a look at a particular example. Right, so we have the polynomial kernel. Okay. So we will only go through the polynomial kernel because that's one that we can understand. Okay, the other things, unless you are strong in mathematics, you cannot understand it. Okay? So what is polynomial kernel? Polynomial kernel is something like this, right? So basically, let's say you have two vectors you want to, original d-dimensional space, you want to take inner product, right? So you will, the kernel function will be of this shape, okay? And so this is actually also here, right? So you can choose RBF, you can choose the polynomial, okay? And when you choose polynomial kernel, you also have those parameters Q. So let's see polynomial kernel, then you have a degree. Okay, this degree is this Q. Okay, by default is cubic. Okay, polynomial function. Right. So this is a Q. And we will look at a simple example where we have Q equal to 2 and D equal to 2. Right. So basically we have this, and because each x is x1, x2, right, so we have the inner product like this. Okay. So you know that A plus B plus C squared is A squared, B squared, C squared. It's 2AB, 2BC, 2AC. Okay. So then you can expand it like this. And so next, you can see something very interesting here. Okay, right? If you think about this, this is really, inner product of two things. Prime. Okay, it's not difficult to see, right? If this 1 times 1 inner product, okay. If this is square root 2 x1 prime, right? This becomes, this becomes square root 2 becomes 2. Okay, this is x1, this is x1 prime. Right, and you can do this, and you can see that each term, if you do the same, it's just its mapping function to two different vectors in the original space, and the result is really this. Okay, so this is pretty interesting because this is just say if we already have x1, x2, right, and we cannot represent something like a circle or ellipsis, right? So now we have the projected term, right? We can represent circle ellipsis in the new space, okay, even just with a cubic equal to 2. Let alone that we actually look at like second learn by default is 3, right? So it's becoming more powerful. Right? You can now, even if you just get 2 features, right, using that support vector machine with polynomial kernel, you will be able to represent shapes like this is the positives as outside the negative. Originally, you cannot do. Okay. Any questions? Yeah. So the most popular is actually RBF kernel. Right, it works well by default. That's why the RBF kernel is the default. Okay. And it's very similar to Gaussian. So if there's a Euclidean distance square, and there's a S is another parameter. So coefficient. Okay, so let me see. So for different kernels, it's the same parameter you will use in different cases. Okay, so you need to read through this and to understand. Okay, so. But I believe that you will be able to figure it out. Right? So just to read through these parameter settings, you will know which one is. This S is one pretty good parameter. In fact, I believe there's a table for that. Let me see. Yeah, so that's, you will find a table listing all the details. Okay, so which kernel, which parameter here. Okay, so there's a table something like this, but we will, because of time, we will continue. So it can be generalized to any distance, right? So for example, you can run some Lanius distance because of the covariance between the features, right? You can use a Hamming distance for like a binary kind. You can also have a sigma model kernel, but for sigma model kernel, it's not always positive semi-definite for certain parameter values. Okay. And yeah, so the kernel. So RBF kernel is actually mapping, mapping to infinite dimension. You can see here it's infinite dimension. Okay, but just each feature is so complicated you don't know what it is. Okay, but once you choose RBF kernel, you are just forced to use those kind of feature transformation. Okay, you don't have too much choice. Right? So if you second learn, it's only those choices. Okay, so finally, let's go to support vector regression quickly. And so, yeah, so in order to guarantee sparseness properly, right? So we only want a few support vectors. We don't want all the rows to come in. Okay, so we do need a loss function, right? So basically we are saying this. So the definition like this, right? So your regression, right? This is the line that you want to regress, for example, right? So the data point with some noise. Okay. What we want to say is if your data is within epsilon noise, you don't have any penalty. If you are within the margin, right? It's a reverse of classification, right? So regression is try to get this line given this point, right? So if very close to the line, we have no penalty. Beyond this line, right? So we can have a proportional penalty. So this is a loss function. We call it epsilon insensitive loss function, okay? Because within epsilon, the penalty is 0. So this is the implementation. If the error, the prediction and the true value is within epsilon, penalty is 0. Otherwise, you have the penalty, but you minus this epsilon, right? Because within epsilon, we don't count them, okay? So the errors are tolerant up to epsilon, which is actually a good thing because, in reality, our measurements always have some error, right? GPS coordinate, right? And error beyond epsilon also just have a linear effect, right? So you can see this is a linear function, okay? It's not like a quadratic, okay? So it's a reverse noise. What does this mean? Let's assume that certain point shoot to here, right? And it's just because of the mistake, some measurement mistake, right? If you use a quadratic loss, right? So this thing will cause a lot of issue, right? So this line will try to close the gap. This line will move up, maybe move up, right? So, but this is noise, right? So if you use a linear function, then there's no situation. So for quadratic data, if you don't have too much noise, the quadratic loss is very good by default. Okay, but you know that your data is quite noisy, right? So maybe among the 100 data, maybe 20 data are totally ridiculous. Maybe you want to use this SVM regression, okay? Because you know that majority is good, but some data are ridiculous. The formation is like this, right? So let me see whether we have time. We only have 2 minutes. Let's try to cover this. Okay. So the formation is very similar, right? So the difference should be within epsilon, but now we have some slack variable. Okay, this slack variable should be larger than 0, larger than equal to 0, and we have a penalty. Okay, and basically, if you are your prediction and y the distance within the epsilon, right? So then the penalty is 0. Okay, otherwise there will be some penalty executed here, right? And the derivation, again, just like take a derivative, this kind of thing. So there's a link. If you are interested, you can read this. It's very similar to SVC, that's SVI regression. Okay. And so for nonlinear kernel, right? So extension. So it's possible introducing appropriate kernel functions. Okay. So again, if you look at SVC, so let me see. Scalar. So not exists. Right, you can still use kernel functions. Okay, all these are still full. The only difference besides C, we have epsilon. Okay, this epsilon is this epsilon. This epsilon. Right. Originally we have a module 1. Now we have an additional epsilon. Okay, that you need to fit. Right. So that's the only difference. And due to sparseness, only a small number of rows have their alpha represented. Okay, so that they are called support factors. And they decide the shape of this line. Okay, so for the details, we don't have time to cover, and you can refer to the link that we show at the very end if you are interested. Okay, that's the end of today's lecture. If you have any questions, feel free to ask. Otherwise, feel free to disconnect. Thank you.
Nice lecture.
Yeah, please go ahead. Praneeth, are you asking questions?
I was saying nice lecture, Professor.
You're welcome.
Hey, Dr. Yan, could you send me the YouTube channel, your YouTube channel?
Oh, yes, but I think it's in the announcement, right? So if you go back to the, let me see. So just to go to Canvas, right?
Hi.
Taking a look.
Yeah, in Canvas.
Dr. Yan, I have a question.
Yeah, go ahead. So each time.
I have a question about the mini project.
About what?
Assignment 3, that's a mini project.
Oh, okay.
And
All right, so yeah, we'll go to that. So basically this, you can go to the here through the link and you can find the channel, right? So you can go there. Yeah, because I haven't finished the previous question, let me finish the student. Just go to each day we share the video, right? So who posts the video you will see, right? So and then this is the machine learning videos for every time, okay? So we share all of them. So is it okay with you? Right, so this is machine learning videos. Okay.
We have a different announcement page, but I'm about to search for your channel. I'll let you know.
Okay, yeah, sure. Oh, okay. So
I found your channel. Thank you.
You're welcome. Yeah. Well, what's the other question? I think the other student, right? Who just asked.
I have a question about the mini project. What library can you use the logistic regression function?
No, you are
library?
implementing it, right? So logistic regression function you can use it for debug. Okay. Are you saying that you want to use scikit-learn logistic regression? This thing, right? Are you saying you want to use this?
Yeah.
No, because we are asking you to implement implement this thing. You just solve this function internally. They are implementing this for you. Okay. So what you are doing is you are implementing this thing. Okay. Right. We are asking you to implement this code in some sense, a small branch of this code. Okay. Right. You just call your library. It's implement all here for you. Right. So what's the point? You can use it for debugging. It's okay. You can call this library for debugging because someone implements this for you. Right. But here in this assignment, we need you to implement a particular case, which is the Newton method, okay, with none.
But I can use the train test split function, right?
Which function?
Train test split function. Split the data.
Oh, that's you can do. Yeah, don't, as long as you don't use the logistic regression model, train test split, those kind of things, feel free to use. Okay.
That means I need to do mathematics.
Exactly. So
code?
Yeah, any second thing other than this model you can use. Is okay. Don't call.
And
don't call this.
The iteration number of iteration is 10. Can you extend that iteration also, or just I have to do 10 iteration? Just.
What the iteration number here?
Means on your assignment you have said that I need 10 trials.
Oh, so 10 trials is not iteration. Iteration is basically when you converge, okay? Because you.
Then what does it mean? 10 trial means what does it mean?
That means cross validation because you have the data, right? So your data you can split. You know, train test split is random, right? So if you look at are you aware this is random?
Sorry.
You are talking about this function, right?
Yeah, I can use that, but
yeah. Shuffle split is random. You have a random state for shuffling. Okay, each time the shuffle is random. You know what I mean? Maybe this time 1, 2, 3 is in the training data set, 4, 5, 6 in the test data set. Next time maybe 1, 4, 5 is in the training data set, right? So you know what I mean, right? So you need to do this 10 times. Is okay?
Oh, so random state is 10. Okay.
Yeah. So yeah, it's not a simple cut, right? It's a randomly shuffle the data and then cut. It's a random state. Okay. Yeah. Any other questions?
Okay. Thank you so much.
You're welcome. Yeah, because for different training set, right? So different way of splitting, it should all work well, right? So you report average, okay? Because maybe there's a particular case that works perfectly, but it's a very particular case, right? So it's more like a p-value, right? So maybe you can find the best case, but you try 100 times, and then that's not true, right? Okay, right? You just pick the best one, right? It's actually overestimate. Okay.
Okay. Thank you.
You're welcome.
Okay. Bye bye.
Professor, I have 2 questions, please.
I cannot hear. What's your question? Can you repeat?
I have 2 questions. The first one is for the tolerance value. Could it be possible that it's going to be negative, or I'm having some bug?
No, it will never be negative because this thing is convex. Okay.
Okay.
The model is convex. When it's convex, you will never have negative tolerance value, right?
Okay.
Yeah, if you have
In,
negative, something wrong in the mathematics and the derivatives. Okay. Yeah, there's some bug.
In, the other thing is for the requirements at the end of the page for the on the assignment.
Can you speak louder? So sorry, can you speak louder?
I'm saying, yeah, for the same the assignment requirements for the at the end of the page it says report on program checklist. I'm not sure what that
program checklist is just, you cannot just throw a bunch of code to me, right? So for example, throw the program code to me, we don't know what it is, right? So you need to say, hey, this code implements this, that code implements that, you run things like this. It's more like
okay.
It's a checklist you submit, right? So this is, checklist to just say, hey, these things, it's a summary of what you did and which file would what. Okay?
Okay.
Any other questions?
I'm just using one Jupyter notebook and it has all the explanations.
Yeah, that's totally fine, as long as you added the annotations, right? So I mean the explanations, because Jupyter Notebook you can write the notes together with the code, right? So you can,
yeah.
Because some students may choose to use R or Matlab, then they have to do, right?
Okay.
So
okay. Thank you so much.
So can a comment on the code, can it be can it suffice for the annotation that you require?
Oh, you can use comment, but maybe we are not reading using IDE. For example, comments typically they should have some color like this, right? But the TA may not using some IDE to read your code, right? So they may not see the comment with different colors. So that's not so obvious. Okay, it's better you have a checklist. Say this is for words, that is for words. Just think about the TA marking 80 of this kind of assignment, right? So they need to go through each one. If you don't do anything to help them to mark, it will be crazy.
So basically, you need another file. You need us to submit another file that explain the code.
Explain what you did, which file, exactly. You don't need to explain every line of the code, of course, right? So you just say, hey, this is the main function you enter, and that's I implement the iterative function for optimization, right? Or if you want to say, hey, these are the gradient with these lines implement this, or something like that. A small description will be good. Okay.
Okay, so the implementation should be fully functional. I mean, do we have to turn in I think is it the HTML running code?
You can submit the HTML, but you need to show that you run through. Okay. Basically, if you use the HTML, the TA can still run it, right? So because the code is there. Right? So but better you also submit the code. So you can save to Python or save to the. If you are using Colab, there's an option, right? You can save to Jupyter Notebook file, or you can save to Python. Right? So you can also include those files, so that TA can repeat your experiment. Okay.
Yeah, I think the reason why I'm asking is, what if the code is not fully functional by the time it's submitted? I mean, the HTML.
It's not fully functional, then we will do that math, right? So, right. So accordingly, we'll see whether your formula is correct, and
But in that case, and I won't be able to generate the HTML. Well, the HTML is going to generate error code and all that stuff.
Then we will deduct points. So because we need to be fair to other students who implement, right? Okay, but we will try to give you some marks by looking into the code. That we will rely on your checklist, right? Your description on what you implement, right? Which part you can. I say the gradient, the application, right? I implement this update function, but I didn't implement something else, right? So you need to describe so that we know how to give you partial mark if you are not able to make it work. Okay. Well, what I'm thinking that we will extend this deadline a little bit because we want to release a solution for the assignment 1. Not sure whether all the students have submitted. We are just giving some safe bands. And we will extend slightly. So because it's Wednesday, right? So we probably will extend to the end of this week, maybe Friday or something. I will talk to the TA to make sure things are okay.
That will help us a lot. I mean, appreciate it.
Yeah, because we haven't released a solution. Maybe some students have the wrong, homework 1, question 4, right? Then you implement the wrong function. That's why potentially you are getting the wrong answer or passing something back, right?
Yeah, because I'm getting an exception that I can't even. I'm trying to debug, and I'm not really good with the Jupyter notebook. So I'm trying to transfer all my implementation to another IDE where I can actually see what the exception is doing.
Got it.
And that's where I'm really stuck right now.
Okay, yeah. So yeah, take your time to debug. Yeah, but the assignment should be independent, right? So otherwise, feel free. Okay. Yeah.
Okay. So when are you gonna finalize the extension? If you're sure about that, I mean,
I will do that. I will do that tonight. Communicate with you.
Okay. Thank you.
You're welcome. Okay. Any other questions? If not, I think Latif, you want to talk to me, right?
Yes, please.
Can you send an email with your Zoom link so I will talk to you?
Okay.
Yeah.
Sure. Thank you.
You're welcome. That's the end for this class. If you have any questions, just feel free to send me an email. Thank you.